Our goal today is to find the electric field at point P for my semicircular arc of charge. And just to be pretty transparent, they probably won't give you a full semicircle, but it doesn't really matter. As long as you know how much arc there is, the procedure is the same. I'm choosing a full semicircle just to make it a little more symmetrical for us. But to get this problem started, let's say that it has a radius capital R, and that there's an entire charge spread out over its surface, capital Q. Our first step is to come up with a way of expressing the charge density of your object. In this case, that's going to be pretty easy. I think we're going to all be able to agree that it's going to be a linear charge density, because it does look like it's a line of charge. So I'm going to use the symbol for linear charge density. So again, step one, come up with the density. The density will be the total charge divided by the total length. So for this instance, that will be Q for the total charge, and the total length would be half of the circumference of the circle. So instead of 2 pi r, it'll just be pi r. This will be our charge density. Now, the reason why we need a charge density is because later on, we're going to be expressing our piece of charge in terms of geometry. So later on in the problem, I'm going to want to replace dq with lambda ds, where ds represents a small length of charge. S is used here because S represents arc length in almost every circumstance. So our goal is to have a lambda we can use here. So now, step two. I want to determine the geometry. They're right outside the door today. I'm so excited. I was watching them as they were watching us, because they don't work between classes. So let's find a piece of charge. I'm going to say my piece of charge is right here, this little section of the arc. And that little section has amount of charge dq. First, I'm going to remind you that the electric field is defined as dqk over r squared. And what I mean by that is this little piece of charge creates an electric field that I will call dE, a piece of the electric field. I'll have to add up all of the pieces of the electric field, but this is just one piece from this piece of charge. I want to remind you that when we talk about determining geometry, what we're really doing is trying to show how a point of this object would behave just like a point charge. There are going to be lots of points on this object, but really we're just adding together all of the different point charges that exist on this object. I'm breaking it up into lots of little point charges. So this particular point on the arc would have this amount of electric field. So I will always start with our standard equation for the electric field from a point charge. The only difference I've made is I've written in terms of dE and dQ, because I know that I'm going to sum over the entire object. That will give me the entire bit of the electric field. It's at this moment when I'm looking at the geometry that I probably should see if there's any way to exploit the symmetry of the object. And I think that all of you would probably recognize that there is. That if there's a point over here with an electric field like this, there is a symmetrical piece of charge over here somewhere that will provide a complementary electric field like that. contributing to what I think will be a net electric field in this direction. How many feel okay with that idea? All right. So what we want to do is twofold. I want to describe where dq is in terms of variables that I could integrate over. And there's actually several ways to do this for a problem like this particular one. The way I'm going to show you is I like to go to the angles when I can. I think angles in trig are pretty easy to work with. So I'm going to see if I can express this based on an angle instead of trying to express it on a pure arc length. So I'm going to make some definitions for what my angles are going to be. So I'm going to call this theta. And the width in here, I'm going to call that d theta. So it's a small piece or small change in angle to go to from one side of dq to the other side of dq. Is everybody okay with that so far? Any questions about that? Because this might be a stretch for some of you, but ds is r d theta. And arc length is equal to the size of the radius times how much arc there is. That's a geometry concept. Is everybody okay with that? This shouldn't surprise you, because if d theta was the entire circle, then that would be 2 pi. And that would just tell me that the circumference equals 2 pi times the radius. You guys following that okay? So this should be a reasonable idea. So that tells me that this piece of charge is located at theta if the center is 0 degrees. And that the size of that arc length is going to be r d theta. Everybody okay with that? All right, so I can rewrite dE and add this to it. First, I'm going to do a simple substitution of lambda ds times k over r squared. I'm making this substitution for dq. Is that too small? And now instead of ds, I'm going to write this as dE equals lambda r d theta times k over r squared. So I've put the geometric part in there. Now I'm going to see if there's any relationship between where I am on the arc and how far away that is from P. But would you all agree that no matter where I am on the arc, I'm always the same distance away from P? So this geometry is pretty easy because R doesn't ever change. So I could rewrite this as dE equals lambda r d theta times k all over capital R squared. How's that? No worries? All right, so we've been able to determine the geometrical part. We've got an expression for a piece of the electric field that is based on where I am on the arc. So that's better. Now, step 3 is I have to deal with the directional properties of the electric field. This is where the symmetry comes in, because the electric field is actually directed this way and I want the piece of it that's directed that way. So I'm thinking I need to use some kind of trig here. Now, based on what I'm seeing, would you all agree that this must also be theta? Is that okay with all of you? Are you sure? Then what function would work best to give me the blue arrow from the red arrow? Do I need to draw that a little bigger for us to see it? Or can we all say it's cosine? We're all okay with cosine? Now, this was an indiscriminate choice. I could have just as easily chose this for theta, and I'd still get the same answer. It would just change my limits of integration, for those of you who are paying attention to the calculus part of this. So don't think that we are stuck with these choices. There's lots of choices you can make. So I'm just going to tack on cosine theta here. So step 3 was deal with direction. Now step 4 is setting your limits. So we have to set our limits of integration. This isn't as hard as it sounds. We just need to make sure we cover the entire geometry. I think theta has to start at 0 degrees right here and has to go all the way to 90 degrees. Is that okay with you guys? But that only covers half of my arc. But since I'm going to have a symmetrical half on the other side, I have a choice. I can go from, say, here, negative 90 to positive 90, or I can go from 0 to 90 and just multiply by 2. Now, if you want my opinion, this is not because I know a lot more than you guys, but my experience in going from negative 90 to positive 90 is that in calc you can end up with a trap. And you guys know why that's true, especially the trig functions. I mean, if you do your trig function and you end up with, say, cosine in your answer, the negative 90 to positive 90 just gives you 0 to 0, and that seems weird. I'm sorry, if you get sine in your answer. So I tend to always, if you can, break a trig function in half that's going to go from 90 to negative 90 and double it. That's just what I usually do. And you'll learn in trig that there are different ways to deal with the limits, but that's how I'm going to deal with this, which means I'm going to go to a different page for just a minute. There. Step 1, you had to find your density. Step 2, determine the geometry. Step 3, deal with direction. Step 4, set your limits. And step 5 is actually to integrate. Step 6, you don't always get to do. But step 6 is usually substitute for the density. That typically is what you'll have as your final step. Substitute in for the density. Our density was Q over pi r. I'm going to look at my function, dE, which equals lambda r d theta k cosine theta all over r squared. And I want to figure out how to add up all of the lengths. Now, this part is, I don't know if you guys are as, I don't know, like as cross-eyed as I am looking at that, but that's actually not nearly as complicated as it looks. I want to point out, everything that's a constant has nothing to do with the integration, or has nothing to do with the calculus. This is a constant, this is a constant, this is a constant, and this is a constant. The only thing that actually matters here is the cosine theta d theta. This is the only part that's actually going to be involved in the integration. Everything else, lambda r k over r squared, is a constant. What I want to be able to do is I want to place the integral symbol on both sides of my equation. It means to add up all of the pieces. So this side is pretty easy. When I add up all the pieces of the electric field, I should get the electric field. The other side, on the other hand, harder to do. It requires that you know calculus to do so. But this symbol for integration requires limits. Where do you begin looking at your piece and where do you end? Our piece was an arc, remember? We're going to start at the middle, which when measured from here is 0 degrees. Or in this case, I think I'm just going to go with 0 radians. And I want to add up every piece of arc from here all the way to here. So I tell the integral to start at 0 and go to pi over 2. Pi over 2 is 90 degrees. And then, because there's two sides, I'm going to double it. Now, a lot of you have not seen this before. And because of that, I want to show you a couple things. Just so you guys understand the way integrals work. There's a lot going on. First, just the integral part that we had was 0 to pi over 2, 2 times cosine theta d theta. I could have also done negative pi over 2 to pi over 2, cosine theta d theta. That would be okay. Also, it's a summation. Summations can be broken up into pieces and added up a couple pieces at a time. So I could have said negative pi over 2 to 0, cosine theta d theta, plus 0 to pi over 2, cosine theta d theta. All of these things are the same. Since a summation is quite literally a sum, I can break a summation up into pieces, little sums, if that makes it easier for me to integrate. So all of these represent the same sum. You pick the one that you think will work best for your circumstance or for your skills. All of them have out front whatever the collection of constants was. They are not part of this integration. Now, the actual integration requires that you know how to do this, and some of you don't, some of you do. You would need to do 2 steps here. And for those of you who know calculus, because you've already had a course, you know that you're going to take this part and find the antiderivative of the function with respect to the variable named. That's our variable named, d theta. So we're going to find the antiderivative of cosine theta with respect to theta. And for everybody who's had calculus, that's like a cakewalk. It's sine theta. But if you've never had calculus, you have no reason to believe that that's true. But I'm going to rush you. For right now, I will not require that you know the calculus portion. But I will require that you will follow the calculus with us. And for those of you who do know the calculus portion, I expect you to be working your calculus. Does everybody understand? I'm not asking too much. So the antiderivative of cosine is sine. So step 1 in doing an integration like this is you have to find the antiderivative. Sometimes you will need a trick. you'll need something to help you, like integration by parts or substitution or something like that. There's lots of tricks in Calculus 2 for integrating, just like there were tricks for doing the derivative. But for the time being, I'm only going to give us ones I think we can do together. And this one is sine. So I'm actually going to use this as my beginning part. And I'm going to say that the antiderivative of 2 cosine theta with respect to theta is 2 sine theta. So your step 1 is find the antiderivative. I'm putting parentheses out front because our next step is to remember that we have limits of integration. And we have to apply those limits. Now what that really means is that we have to take our new function, whatever that antiderivative is, and place in it each of our limits. So basically, we apply our function from the final limit to the original limit. So this will be 2 sine pi over 2 minus 2 sine of 0. So you take this limit, put it in first, and subtract this limit. Luckily, sine of pi over 2 is 1, and sine of 0 is, so this whole thing becomes 2. Not the answer, by the way, because we still have lambda r k over r squared, right? The constants that were out front, the things that we took away. So this represents the electric field for that half a ring of charge. And I'm just going to rewrite it. The r cancels with one of the r's on the bottom, and you get lambda k over r times 2. So our final answer, E, equals 2q k over pi r squared. Now, that's the electric field at a very specific point. It was not particularly complicated, but that's because every point was the same distance away from P. That's what made it a little bit easy. But you guys see that this process can be really convoluted and really challenging. And we just did, unfortunately for you, the easiest example. Every example is more complicated than this. Now, luckily for us, there's just not that many examples we get to do. Yes, sir?
Why is it r squared?
Lambda is q over pi r, and there's already an r in the denominator. And just a couple of FYIs here. You notice the r squared in the denominator, it's not accidental. Remember, we're always comparing this to qk over r squared, right? Our standard form for the electric field from a point charge. Do you guys see that we have glimpses of that here? That if you take a look at what's circled, we have a glimpse of what's there. Now, what's interesting is 2 over pi is less than 1, right? It's about 2/3. So if you think of the shape that we had for just a minute, but it does have a scaling value in front of it. And the fact that pi worked itself into something with the circle, not a surprise, right? Hit pause. Because there's no way for me to take the total charge and divide by the total length if the length is infinity. So generally, when we're given an object that has infinite size, we're usually given a charge density to go with it. Now, I want you to be a little careful the way I say this, because although this might be an infinite line of charge, there are times when a finite line of charge can be treated as infinite. And generally, that's when you're very close to it compared to its size. So if you're a millimeter away from a meter-long line of charge, you're okay treating it like an infinite line of charge. And that will happen on the exam. They've done it all the time. But note that you're going to need a way to express the charge density. Generally, for something that's infinite, they will give you a value to use as the charge density. So we're going to assume that the charge density is lambda. Our infinite line of charge goes off in all directions. We are a distance z away from that infinite line of charge. So our step 1 is done for us. Our step 2 is to deal with the geometry. I'm going to pick a point right here. Call that dq. I want to see if I can find a way of defining the electric field from this piece of charge. So we're going to need to come up with a way of describing this point. I think it wouldn't be too crazy to assume that there's a point on the line that is a perpendicular distance z away from where I am, and call that 0. And maybe label this distance x. This does a couple things for me. First, it gives me a way of expressing how far away I am from my piece of charge. I need geometry to tell me where that piece is. Remember, my thing starts with dqk over r squared. I need to try to work in z somehow. One way to do so is define r in terms of z. It also gives me a way, perhaps, of dealing with this piece of, this length. So I could say that this length is dx, which will mean that dq equals lambda dx. If I bring those pieces together, I can write lambda dx times k over what looks like z squared plus x squared. Now that works pretty good, except that, do you realize we're going to need to deal with the angle here too? We'll do that tomorrow. Our shape was a semicircle, and we were looking at a point right here. We're saying that the electric field here at this point is about 2/3 of what it would be if all of that charge was concentrated right there. Does it make sense for it to be less? Sure, because there's some parts of that charge that canceled out. So it has the same form.